Hi, Dr. Revis here with Watch Me Work It. In this Watch Me Work It, I'm going to carry out some calculations involving limiting reactant, amount of product formed, excess product used, and the percent yield, along with how to balance the equations related to these. So let's get going with this one. Consider the following reaction. We have copper 2 chloride reacted with sodium nitrate to give copper 2 nitrate and sodium chloride. Here we show you the molar masses that I've taken liberty of calculating in advance. If you're unfamiliar with how to calculate molar masses, see my other videos on this topic. So here's what we have. We have 16 grams of copper 2 chloride and 21 grams of sodium nitrate, and we want to carry out this reaction. When we're carrying out a reaction like this, it's important to note that you will have to carry out two-dimensional analysis calculations, considering each of these masses to be a given. And here's what you want to first of all do. You want to balance that equation. After balancing the equation, then to find the number of grams of sodium chloride or copper 2 nitrate, if that's what you're interested in, form, you'll carry out dimensional analysis again of both givens. Let's start then by balancing this equation. Ready? Here we go. So to balance this equation, we take a look by inspection. I'm just going to go ahead and do this really quickly. If you want to learn more about how to balance equations, see my other videos. So here, if we look at this, we have 2 chlorines on the left side. So I'm going to need to put a 2 right here that takes care of those chlorines, but it adds 2 sodiums. So I'll go back and need to put a 2 here that takes care of 2 sodiums. I have 2 nitrates on this side, 2 nitrates on this side, over 6 oxygens and 2 nitrogens, or 6 oxygens, 2 nitrogens. Now it's balanced. So now that you have the balanced equation, now you can start to do your work. And remember, to carry out a limiting reactant problem, you will have to do two-dimensional analysis of both givens. So you treat them as two independent problems and compare the results at the end. So let's do that. How many grams of sodium chloride are formed? In this case, I want to find sodium chloride. I could have looked for copper 2 nitrate as well, but in this particular video, I'm interested in sodium chloride, table salt. So if we want to determine how many grams of sodium chloride are formed, we have to consider the limiting reactant, and that will tell us the excess reactant. Ready? So watch me work it. So let's do a couple of givens. First given is 16.1 gram of copper 2 chloride. We do set up a dimensional analysis relationship. Grams copper 2 chloride on the bottom to moles of copper 2 chloride. And we continue this dimensional analysis to moles copper 2 chloride. And right here is where we make our change, mole to mole ratio of what are we interested in? Yep, sodium chloride. And we really want to get to grams of sodium chloride, so we say moles. This is a dimensional analysis relationship, math ratio. Here, a conversion factor, mole to gram, sodium chloride. So let's go ahead and put these numbers in. The gram per mole is copper chloride. I've already taken the liberty of calculating that. So we have 170.48 grams to every 1 mole. That's it. This is a molar mass. We simply look up and calculate the molar masses. We don't care whether it's in a balanced equation or where we get it from. This is the molar mass. Then we look at the mole to mole ratio here. This comes from the balanced equation. We simply look in front of sodium chloride and put whatever value is there. And it's a 2. In front of copper 2 chloride, we see there is no value there, which means there's a 1. And here we have gram per mole ratio. That's molar mass. We don't consider a balanced equation. We simply go to the periodic table, look up sodium, look up chloride, and we'll get this particular molar mass. I've already done that for you. So here we write it here, 0.34 for every 1 mole. That's it. And if we check our crossouts in the math equation, we'll see that it worked out nicely for us. And so we're going to punch this through on our calculator. And if we punch it through, we get this number to 3 sig figs. Since this was 3 sig figs, I'm going to finish my answer with 3 sig figs. So I'm good there. So that's 1. Now, we're not done yet, because we now have to compare this against the other possibility that gives us sodium chloride. That reagent is sodium nitrate. And so we carry out a dimensional analysis here by writing our given. We always start this out with our given, no matter what, grams of sodium nitrate, 3. We do a times bar here for the dimensional analysis ratio. Since we have grams here, we transfer automatically here without really thinking about it too much because math rules dictate this. And so gram, the relationship is gram per mole of sodium nitrate. And now I'm really not interested in gram in moles of sodium nitrate. So I make a transfer here, and that's mole. Now I can do a mole to mole ratio because that's allowed in chemistry. Same. So here, since we have the same material, sodium chloride, we put it there. And now we do a crossbar here, do a math step, mole down here. Sodium chloride, that's actually Na. Chloride, not very well written, but that is sodium chloride. There we go, close enough. And this is grams sodium chloride. All right, and now we go back and put in all these values, gram per mole of sodium nitrate. I look, wow, I've already calculated that for you. I got all that from the periodic table. 1 sodium, 3 oxygens, and 1 nitrogen gives me that. So there it is. I have that there, right in the molar masses, and we are good to go. And now we need to put in the mole to mole ratio here. And so that mole to mole ratio for sodium chloride to moles of sodium nitrate, we look at the balanced equation. Sodium chloride has a 2 in front of it, and sodium nitrate has a 2. We don't try to reduce them. 2 to 2, gram per mole of sodium chloride is a molar mass. And I've already done that too. That's 39.34 from the periodic table, added up. And when I run these numbers through my calculator, I get 9.86 grams sodium chloride from this way. 3 sig figs here, 3 sig figs here, and I'm happy with my answer. So if I look at this, what we discover then is the least amount of sodium chloride is formed from copper to chloride. Therefore, copper to chloride then would be my limiting reactant. So I would say copper to chloride right here is my limiting reactant. All right. Therefore, my excess reactant would be the other species. Yep, sodium nitrate. All right. So how many grams are formed? That's a pretty important question to answer. The grams formed is 7.43 grams of sodium chloride from this balanced equation here. All right. So now, how about the other questions? All right, so I've taken the liberty of transferring over the data from the other one in a little nicer form for you. These are the answers from the last one. So we're going to proceed on to answer number 3. How much of the excess reactant remain or is left over after reaction? In other words, we had more than the excess reaction, and so the excess is sodium nitrate. And so another way of asking this is how much limiting reactant was used. So if we know how much was used, we can subtract the difference from what we loaded in, and we would get our answer. So let's get going on this one. So we're going to work with this excess reactant here. So, but to do this, what drives any reaction once you've found a limiting reactant is the limiting reactant. So let's use the limiting reactant to limit the amount of excess reactant used. It guides the output of the product. So let's do it. So I'm going to do this all the way over, starting over again with my given. I now know that my limiting reactant is copper to chloride. So I'm going to take the grams of copper to chloride there. So it's grams of copper to chloride. And I'm going to run it through a dimensional analysis. You know how to do that now. So I'm not going to waste your time, but so much language telling you over and over again stuff you already know. This is 170.48 grams every 1 mole. Then these moles will be moles of copper chloride to moles of the limiting reactant now. My limiting reactant was sodium nitrate. I am interested in the output of sodium nitrate that's guided by my limiting reactant of copper to chloride. Let me repeat that again, just in case it sounds a little funny. I'm interested in sodium nitrate, my excess reactant, And that excess reactant is guided by the limiting reactant, copper 2 chloride. So here we go. We look at the balanced equation. How many moles of sodium nitrate? There's my balanced equation again. Great. So my sodium nitrate has a 2 in front of it, and copper 2 chloride has a 1 in front of it. So that's a 2-to-1 ratio. And so now we go moles of sodium nitrate to grams of sodium nitrate. I put in the molar mass of sodium nitrate, which is 84.99 to 1 mole. If I run this through my calculator, my dimension analysis look right, the math is right, the relationships are right, the conversion factors are right, this mole-to-mole ratio is correct because I simply read this from the balanced equation, no fancy math there. I have my molar masses here. That's correct. Got it from the periodic table and did my arithmetic there, and I'm happy. So if I run this through my calculator, okay, it will tell me how much sodium nitrate I should have used in this reaction. That's another way of looking at it. So I should have used this amount of sodium nitrate. That's how much I should have used in this reaction. Okay, I cut off your numbers. 16.1 gram sodium, and that should be a 3. Wow, am I getting sloppy with the numbers here? Okay, so therefore, that's how much we should have gotten, but we used how much? Well, in the beginning, when we started this reaction, we used 21.3 grams of the sodium nitrate, but it only consumes 16.1. If I do a little bit of simple arithmetic that I'm going to write off here to the side, yeah, I'm a little bit crowded here, 5.2 grams sodium nitrate excess. That's overload. Okay, so too much. So that's how much excess we had left after we ran this reaction. Okay, so let's move on to the next one. What is the percent yield if we collected 5.7 grams? So obtain means we collected. We dug that out of the kettle or out of the flask, and that's what we had. Now, that means we need to know the theoretical yield. Well, the good news is we already have a theoretical yield. The original amount formed from the limiting reactant is the theoretical yield. So as soon as you find your limiting reactant, make a little note. Say, this is my theoretical yield. You'll need it later in most of these calculations. So let's just take that theoretical yield and let's see if we can do a little math with it. Percent yield equals actual divided by theoretical, always times 100. So the actual yield was 5.17 grams. The amount I should have gotten was 7.23 grams times 100 gave me a 69.6% yield. And for all of you who like these little squiggly approximations, that's about 70%. Not very impressive, but not bad at all. So there you have it. Doc Revis, limiting reactants.